is that focused? I don't think it is at all. And maybe we should write a little bit more. Okay, so let's start off center of mass. And this is the WebAssign number 4. Focus on that now. There we go. So we've got the curves. Y equals e to the x. Y equals 0. And x equals 0. And x equals 4. And again, you guys might have different numbers. It looks like that number might change for people. So first step, sketch the region. So because we have y equals 0, x equals 0, and then e to the x, and then we're going from essentially 0 to 4 on the x-axis. And of course, the y coordinate will be e to the 4th there. So we've got essentially this region. Where is the center of mass? Well, you can eyeball it at first and just kind of get a general idea. There's more mass concentrated to the right, so it should be slightly to the right, and then there's more mass concentrated to the top. So the center of mass, I don't know, I'm guessing is going to be something like there. So how do we find that by hand? Let's see. So they don't give us a density or anything like that. We assume that it's uniform density, and we aren't going to have to really worry about density at all. So what is our mass? Mass is just going to be the integral of density over the area. So density times area. Density is constant. And so we just need to figure out how we're cutting up the area. And since we're typically slicing up our x-axis, like all of the integrals pretty much we've done so far, it's just the integral of the function dx. And so we can fill all that in. Density times our function is e to the x, so that's the height, times dx. And we're going from 0 to 4. And so what do we get? Easy integral, rho, e to the x, 0 to 4. So we're going to have rho times e to the 4th minus 1. And I'm just going to keep it like that. If you want, you can ignore rho as long as the density is constant, as we'll see, because that rho essentially is going to cancel out. So what do we need for the x center of mass? The x center of mass, so following the generic formula, looks like this. The moment about the y-axis divided by the total mass, which we just found. So all these center of mass problems, I always find the mass first, just because it's usually the easiest integral, and it's always in the denominator for both the x and the y coordinate. So since we use it sort of twice, I always find it first. If you kind of forget the generic formula, really what this is, we just take the same integral for mass, and now to find the center of mass, you have to consider that, well, if I want a balancing point and find like a point where this whole thing will balance on a pen or something like that, then, well, the distance matters, right? If we want to find the x distance, not only does its weight matter, but the distance it is from that point. And of course, we actually just weighting it from any arbitrary distance or the distance from any reference point, and then averaging will essentially find the center. So all we have to do is weight the same mass integral by an x. So we'll essentially have x times rho dA. And then in the denominator, we still have this m. And so, of course, this moment of about the y-axis is what we call this integral. And so that's our just next piece. And you see that the rho is going to come out. It'll cancel with that guy in the denominator. So let's just take a look at the integral of x dA. And actually, let's just keep the rho outside. Same integral, same functions. We just got an extra power of x. So we'll have rho x times e to the x. And we are integrating from 0 to 4 dx. And of course, now with the extra x's, our integrals get a little more technical, a little more complicated to do. So we just got to remember all of our techniques of integration. This guy, hopefully you guys recognize, integration by parts. We want to take a derivative of that polynomial part, and that extra x. So our du is just dx, our dv, e to the x, and our v, e to the x. And so what do we have? We've got our rho times the integral of x e to the x minus the integral of e to the x. I'm just going to save the bounds for later. So we'll have rho x e to the x minus e to the x, simply because that integral was easy enough to just get through. Bounds are all the same, 0 to 4. And then when we plug that in, we'll get rho times 4e to the 4th minus e to the 4th minus 0 minus 1. So simplifying there, looks like I'm running out of space here, but I think we can squeeze it in. We just got rho 4 e to the 4th minus e to the 4th is going to be 3 e to the 4th plus 1. And so that was this top. That's our moment. So it's not our x bar yet. To find x bar, let's pull up what we had. So our x coordinate for the center of mass is then going to be this rho times 3 e to the 4th plus 1 over the total mass, which we found was rho e to the 4th minus 1. So just 3 e to the 4th plus 1 over e to the 4th minus 1. So nothing too tricky with this, hopefully. As you're saying, it's kind of just a lot to do because we still got to do the y coordinate. But nothing fancy in terms of setting up the integrals, no finding, specific geometry or anything like that. You just have to kind of recognize the curves and then remember to weight the x integral by an x and then divide by the mass. So likewise for the y, I'm going to write this out, but we use kind of a trick in Calc 2 for the y. The y's are always a little bit more complicated than the x's in Calc 2 because we don't know how to do double integrals yet, which you'll learn in Calc 3. It's the same concept though. We want to find the y center of mass. So just as I was doing that with the x's, well, as each piece, if I want to know sort of the contribution of that little block to how it's going to cause this plane to tilt based off of where the center is, I need to know sort of both its x distance and its y distance from a center, or at least keep them all relative to a reference point. And then so with our averaging that we're doing, we will find the center y coordinate. So how do we deal with this in Calc 2 now? Well, I want to integrate with respect to x. And so relative to these slices, if this is my slice. Well, it has a height of y. What is the average y value on just that slice? It's going to be right in the middle. So it's going to be 1/2 f of x. And then our dA is still just f of x dx. And so this is just a formula you can use. You don't have to rederive it every single time. But we just want to integrate the square of the function to find the moment about the x-axis. And I forgot my density there. It's going to hang out because it's constant. But of course, again, it'll cancel with that density in the denominator. So it's not terribly important to keep your densities around. As long as you keep it out of both the mass and the top integrals if you want, it's fine. It's really just the area weighted by the y's divided by the area of the total space. Okay, so in this problem, what do we got? We'll have 1/2 rho. Our f of x was e to the x. We want to square it, dx, and we're integrating from 0 to 4. And this will just be the top integral. So this is our moment about the x-axis. And this one's not too bad, because that's just e to the 2x. And so our integral is going to be 1/2 rho times another 1/2 e to the 2x, evaluating 0 to 4. And then what do we get? 1/4 rho. And we'll have e to the 8th minus 1. Which means our y center of mass, 1/4 rho, e to the 8th minus 1. And then our mass, again, was e to the 4th minus 1. Rows cancel. Sorry, let's write this a little more nicely. So the 1/4, I'm just going to put the 4 in the denominator. E to the 4th minus 1. E to the 8th minus 1 in the numerator. Pretty much done there. If you want to be fancy and cancel, I don't know how technical WebAssign is with making you guys cancel. It doesn't look like, it looks like it'll accept that answer. Of course, e to the 8th minus 1, we can write e to the 4th minus 1, e to the 4th plus 1. A difference of squares over 4, e to the 4th minus 1. So those guys cancel. And we'll just get 1/4 times e to the 4th plus 1. You guys see that, or am I running off? Looks like I'm running off a little bit. Any questions on those guys? All right. So to give you guys a little bit more for homework 6, I think I did one of the work problems for you guys. I was looking at some of the sequence stuff. I'll give you some tips. And then if you want, come to office hours on Friday. We can talk about office hours on Friday. I don't know, maybe tomorrow. Since it's Friday, I'm sure most of you guys wouldn't like to work too late. myself included. So I would prefer to probably have office hours earlier, maybe after class. I don't know, but my office hours, my Fridays are also really busy. So we can talk about it either tomorrow or Friday, depending on how much progress you guys are making. So homework 6, this is just some sequence stuff. Let's kind of shift our gears a little bit and do a little bit of sequences before we jump into series. Homework 6, number 6, we want to figure out if a series converges or diverges. And I want to do a little bit more practice with these factorials because these are complicated. We saw one example with a factorial, and then in like the denominator was n to the n. Well, now I have n factorial over e to the n. And so the question is, what's the limit if it exists? And again, with this one, we can't quite use our normal functions because we've got this factorial in it. So we've got to do a little bit more fancy algebra. We can use a little bit of squeeze theorem, and then we'll have to use some algebraic techniques as well to deal with the factorial. One thing we have is that the sequence is always positive. It's one thing that should be pretty immediate. Since there's no minus signs going on, of course, I'm always starting at 1, so we're putting in positive numbers. Oh, that actually brings up a point. What happens if we start at 0? This might come up on a web assignment. Use this as a fact. 0 factorial is 1. It's kind of weird to think about of why 0 factorial needs to be 1. In some sense, you can kind of think about it as if we just had a gamma function, the actual function that models factorials, it's what it needs to be. There's some other arguments for it, but I don't want to get into it. Just use it as a fact that if you ever see 0 factorial, it's 1. So it's not undefined. Okay, so let's get back to the problem here. And we have e to the n. Well, e is not a nice number, right? Because it's 2.718. So one thing we can also say is if we want to get a little bit closer bounds for this guy, well, what happens if I make the denominator bigger? So e is about 2.718. Let's replace e with integers. We'll replace it with 1 above and 1 below because those are nicer to work with. And that'll just give us a sense of how to work with this and do our comparison. So if I make the denominator bigger, I get a smaller function. So I get something like this. Can you guys see that? I feel like there's a weird shadow from the camera. Maybe I'll try to angle it a bit more. And if I make the denominator smaller, we get something bigger. So these are going to be our closest comparisons. And so by analyzing these guys, we can try to figure out more of what's going on with here. And so let's start with the left guy. Let's just give it a name. Let's call this guy AN, since our original guy was CN. So what's going to happen with this? Again, our n factorial is n times n minus 1 times n minus 2, all the way down to 1. 3 to the n is just going to be 3 times 3 times 3. We're going to have a bunch of 3's. So what do you guys think is going to happen with this guy? Converge or diverge? Any ideas? What's happening in the denominator? All of these terms are the same. And the last one we saw, it was n times n times n times n. And those n's are going to get bigger as n increases. But in this case, we're just adding more of the same number, I guess multiplying by more of the same number. And perhaps if we wrote it an extra term there, as soon as my n is 4 or more, this chunk is going to keep increasing because the numerator is always bigger. And so this term's bigger than 1, that term's bigger than 1, that term's bigger than 1, that term's bigger than 1. Whereas this is a fixed value. I can compute that, right? 3 over 1, so it looks like 2/3 times 1/3. It's always going to be a fixed 2/9. And then what's happening with this term? This term is going to go to infinity as n gets bigger. Does everyone see that? Because the more n's I have, I'm just multiplying by a number again that's bigger than 1. Consider what happens like if n was 6. Then it's 6 divided by 3, then it's 2. If n is 30, then it's going to be that sort of ratio. 30 over 3 is 10. And so I'm multiplying by 10. And so we're just going to be multiplying by bigger and bigger numbers. So our an goes to infinity. And this is enough by a comparison test because by a similar argument, we can actually show that this guy goes to infinity as well. But because our lower bound goes to infinity, anything bigger than that also has to go to infinity. We can plug in our limit expression. So the limit as this guy goes to infinity has to be bigger than this limit to infinity, which means that the limit of our original sequence, well, if the limit of our original sequence is bigger than infinity, it itself has to be infinity. Okay, so one last thing I wanted to cover, at least on factorials, was how do I deal with ratios of factorials now? So let's look at a similar problem. I want to know, does this converge or diverge? We've got 3n plus 1 quantity factorial and the quantity 3n minus 1 factorial in the denominator. So how do we do this? Of course, if I take the limit as n goes to infinity of this sequence, we'll get infinity over infinity, and we can't do L'Hopital's rule with these factorials in there. So our algebraic trick with this guy is to consider writing out a few terms. One thing to note that is if the numerator, if we have 3n plus 1 factorial, what does that mean? That means 3n plus 1 times, well, the next term when I subtract 1 is just 3n, times 3n minus 1 times 3n minus 2, and it's going to keep going. Likewise, 3n minus 1 factorial is 3n minus 1, 3n minus 2 times 3n minus 3, and it's going to keep going. So notice now that with the numerator, 3n plus 1 factorial, we have 3n plus 1, 3n. Then I have the same sequence, 3n minus 1, 3n minus 2, 3n minus 3. And that's going to keep going. So the trick is with dealing with these factorials is you can always write the bigger one. So 3n plus 1 is always going to be slightly bigger. I can factor out the first two terms, 3n plus 1 times 3n. And then what remains is now 3n minus 1 factorial. Does everyone see that? So let me write that. I'm kind of running into the wall there. Really, if we wrote all this out, we'd have 3n plus 1, 3n, and then all the factorials, 3n minus 1, 3n minus 2, all the way down to 1. Whereas the denominator, I've got 3n minus 1, 3n minus 2, down to 2 times 1. So you can write it all out if you want and then recognize that, well, everything in the denominator is going to cancel, and the only thing left in the numerator is this guy, 3n plus 1 times 3n. Or if you start to get comfortable playing around with these guys, you can recognize that, well, all of this expression that I sort of had left in the numerator, once I factored out these first two expressions, I can shorthand that by 3n minus 1 factorial. Then that whole quantity will cancel with the whole denominator, essentially like we did in this step here. Except here we kind of did it term by term. Here we kind of just grouped all of those terms together and then canceled them all at once. And so what is left just those two terms, and now what's going to happen as n goes to infinity? That whole thing will just go to infinity. Any questions on that? Okay. So let's jump into, let me try to keep my notes organized. Series. So what is a series? The way you want to think about series is, in some sense, they're just like infinite integrals. And actually, we'll see that once we come up with a, there's my notes, sorry. When we start doing the integral test, which we'll see tomorrow. So a series is just an infinite sum of all terms in a sequence. And so we write it like this. So you guys are somewhat familiar with sigma notation. So this sideways guy there is Greek letter sigma. Of course, we've seen it come up in Riemann sums. And so it just means add up all the terms from 1 to infinity where my terms are given by the expression an. So whatever my sequence an is, it just means we are literally adding up everything. We are adding now an infinite number of values. And so it kind of poses a question, well, how can we add an infinite number of values together and still get a finite number? So we'll start taking a look at least geometric series are kind of the first basic example of how that's going to work. In general, though, the way you want to think about this is that a series is to a sequence as an infinite improper integral is to a function. So in our previous lectures, we kind of saw how sequences we really want to think of as functions. But now maybe we have some fancier algebraic operations that we haven't quite seen with our nice kind of continuous functions that only apply to these discrete functions, which is really what sequences are. And so now adding up all the values in a sequence is going to have very much the same properties as these infinite integrals that we had with functions when we're integrating functions all the way out to infinity. It's really going to depend, convergence at least, will really depend on the decay of the function, how small the function is getting. So in other words, to give a little more concrete example, if we want to take a look at a sequence of just 1 over n, this is called the harmonic sequence, and we'll be looking at that a little bit today. It's very much the same as considering the integral from 1 to infinity of 1 over x dx, or potentially even 0 to infinity of 1 over like x plus 1 dx. You want to consider these as behaving pretty much the same. And we'll see why a little bit more tomorrow, and how we can model this guy with what we call the integral test, where in some sense the convergence of the integral of the corresponding function will also converge, or will also depend on the convergence of the sequence. Those two things go hand in hand. So for now, let's just try to introduce more of how we're going to study these and some of the basic examples of how we can get convergence out of them. And moreover, what does convergence even mean? So we talk about convergence by what we call the sequence of partial sums. And, well, what do we mean by that? If I write a sum as n equals 1 to infinity of an, well, we didn't like dealing with these infinities with these integrals. You can kind of consider it as the limit as t goes to infinity of the sum of the first t values. And this guy here is what we consider a partial sum. We would call this, often use S. In this case, it would be S sub t. So in other words, our S sub t, instead of adding up all infinitely many terms, S sub t is just saying add up the first t number of terms and see what you get. It's a finite number because we're adding up only finitely many terms. But then, so we get a sequence. So now we just have a sequence of S1, S2, S3, and we want to see is if the sequence ST converges If and only if. This infinite sum converges. In other words, by converges, I mean is a finite number. So this is our definition. That means that I can add up an infinite number of terms given by an and get a finite value as long as the sequence that I get by taking more and more successive terms and adding them together also converges. So, for example, is anyone still writing? You guys good? Okay. Let's take a look at that harmonic series. So let's take a look. What is S1? S1 is just 1 over 1. S2 is going to be the first term, 1, plus 1/2. Oops, 3/2. S3 is the sum of the first 3 terms. 1 plus 1/2 plus 1/3, which mental math is going to get a little tricky here. So the first 2 were 3/2 plus 1/3 is what? So 9/6 plus 1 or plus 3. Excuse me, plus 2. So 11/6. And S4 is going to be 1 plus 1/2 plus 1/3 plus 1/4. And what is that? So it's going to be our first 3, 11/6 plus 1/4. And what's that going to be? So 3 out of 12 plus 22 out of 12. So 25 out of 12. And so we get this new sequence. Let's write it out, at least the first few terms. We had 1, 3/2, 11/6, and 25 over 12. And then it's going to keep going. So that's our sequence of partial sums for this guy. And it's only if ST converges, then we would say that the sum converges. Likewise, the same statement holds for diverges. Unfortunately now, coming up with a closed form expression for more and more successive terms might be very hard. It's even harder for these types of sequences that we get than some of the ones we've already seen. So we may not be able to find an expression for the general term. So finding out whether it converges or diverges, usually you need some sort of fancy trick. And at the moment, about the best we can kind of do is either numerical analysis, by keep taking successive terms In this case, you might need to use a calculator once you get bigger and bigger to make a statement as to say, well, do the numbers look like they're getting bigger and bigger? Is this going off to infinity? Or does it look like it's going to a finite number? Or we have to do some sort of algebraic trick. So let's take a look at what's going on with this harmonic series. Diverge or converge? What's your intuition? You should always make a guess first and start to develop an intuition.
Diverge, because we
Diverge,
keep adding one.
What'd you say?
Because
Diverge.
we keep adding one.
Yeah, because you can formulate it in such a way that you keep adding one. Exactly. And we'll see how to do that. The other thing you can kind of get an intuition for is what's going on with this integral, right? We saw the integral of 1 over x, and when I integrate that out to infinity, even though x is getting smaller, still diverges, right? The area under this curve is infinite. So how do we show that for this sequence? Let's write out our general term. S sub t is going to be 1 plus 1/2 plus 1/3 plus 1/4. And how many terms do I want to write? I think we got to keep, let's write out a few more. 1/5, 1/6, 1/7. And we'll stop there. We'll keep going. All the way out to S sub t. And actually, we can even kind of keep going and think that that's going to keep going out to infinity. And so what is going on with this? We want to group powers of 2, number of terms. So the first term, the next 2 terms, the next 4 terms. The next one would be the next 8 terms. Starting with 1/8. And we can bound those. So this guy is going to be, did I do this wrong? I think I did.
Yeah, because you got to do 1/2, 1/3, and 1/4.
Yeah. 1/2 plus 1/3 and 1/4. Let's write it out again. You got to do fancy tricks with these, and it helps to see them and work through them. So I'm going to bound, yeah, those 3 terms, and then plus 1/8. And actually here, let's bound these 2 terms. So we're just going to add consecutive powers of 1/2. So this is going to be bigger than 1 plus 1/2. And now I have these 2 terms, 1/3 and 1/4. Which one's the biggest? Is 1/3. So if I replace that 1/3 with something smaller, this term sequence, the series, is smaller than that guy. So we have a greater than on that side. Likewise, here I have 4 terms. The smallest one is 1/8. If I replace them all with 1/8, we get something bigger. But now what is this when we add it all up? Sorry, that's equals to 1 plus 1/2. These 2 terms are 1/2. Oh, I'm off the page. Sorry, guys. These 4 terms are also 1/2. And then likewise, we can keep grouping in such a way that we're adding on a constant number. And what's going to happen if I keep adding a finite number to itself? 1/2 plus 1/2 plus 1/2 plus 1/2. It's just going to keep getting bigger every time I add 1/2. So this guy diverges. By bounding our sequence of partial sums. Okay, let's consider another one. Let's write the sum of 1 over, you can either write it as 1 over 2 to the n, or you can think of it as 1/2 to the n. Of course, 1 to the n is always going to give me 1. N equals 1 to infinity. So this is our geometric series now. So we saw geometric sequences because what's happening, we essentially have a geometric function in there. It is multiplying by this factor of 1/2 every single time. So do we think converge or diverge? You want to kind of think of this as something like 1 over 2 to the x. And remember when we saw integrals of, so just kind of as an aside, when we saw this integral of e to the minus x, this guy converged, right? And this is the same as 1 over e to the x. So as long as the base is bigger than 1, this guy will converge because these exponential functions increase very rapidly, which means if they're in the, if they're in the denominator, this whole expression, that whole fraction is going to decrease very rapidly. And we will be able to find a finite area. Why do we call this a geometric series? Anyone know? Let's consider this problem. Suppose I have a box. Say the side lengths of the box are 1. What's the area of the box? 1, right? 1 by 1. Okay, well, let's say I cut the box in half and now only want to consider the area of half the box. We'll call that A1. And then now I only have another half remaining, and let's suppose I cut that box in half. So now we have a different area. We'll call that A2. It's now 1/4 of the box. The sum of the total area is going to be, well, I added half the box, now plus 1/4 of the box. What's the next piece going to be? So now I've got a remaining 1/4. If I cut this guy in half, and add that guy in, we have now 1/8 of the box. And I keep doing this. I just keep taking whatever we have remaining and I cut it in half. And we add it in to the total area. What's going to happen as I do this an infinite number of times? Let's do this one. What's the total area we get? We get a total area of 1. Since eventually, as I keep cutting this box up, I will eventually ad infinitum exhaust all of the total area of the box. And that's what we'll get. And you should recognize that this series is just what we are denoting by that expression there. So there's a very kind of geometric nature about slicing things up into a third, into a half, based off of whatever ratio we have there. How do we deal with this in general? So general test, or so. Actually, let's first state our divergence theorem. We'll get back to geometric series just a second, and how, well, what happens if I change, instead of 1/2 to the n, I had 1/3 to the n? How do I figure out what that converges to? It's a little less intuitive, because if I start with a box again, now cut it into a third, and then I have 2/3 remaining. Cut that into a third, and then the numbers get a little bit harder, and it's a little bit harder to see, well, do I actually cover the whole box if I cut it into thirds that way? With cutting it in halves, it's kind of clear that, well, eventually we will cover the whole box, so the total area is 1. But if I cut it into thirds or even smaller pieces and only shade in one piece at a time, it's not necessarily so clear that we'll end up covering the whole box. So, big thing to note. In both cases, the sequences went to 0, converged to 0. So that is our 1 over n, as n goes to infinity, is going to 0. Likewise, our 1/2 to the n also goes to 0, as n goes to infinity. Just the sequences. But only one converged, only one series converged. So it turns out that the sequence going to 0 is going to be a necessary condition. If I want a series to converge, then the sequence of terms, of individual terms, has to go to 0. And hopefully that should make sense, that sort of by our harmonic series example, that I can't add up a constant number. If I'm adding up a constant number, 1 plus 1 plus 1 plus 1 plus 1, the more ones I add up, the closer we're going to get to infinity. We're just going to get bigger and bigger numbers. Even if I'm only adding up 1/2, 1/2 plus 1/2 plus 1/2, the more times I add 1/2, it's still going to go to infinity. So in order to get convergence, we have to have that the individual terms go to 0. Unfortunately, it's not enough. Even if the terms go to 0, sometimes a series won't converge. And this is our test for our divergence. So the divergence simply says that for a series, if, let's say, the limit as n goes to infinity of an, if it does not equal 0, then the series itself diverges. So one of the first questions we want to ask ourselves is this. So when we're given more complex problems about series and asked, will the series converge or diverge? This is the first thing that should come to mind. Always check if the terms go to zero, because if they don't, it diverges and we're done. No work is needed, no algebra, no fancy tricks, and computing a limit or computing the sum of a series, because the terms don't even go to zero. We're just going to be adding up a bunch of non-zero terms. It will diverge. But of course, we should have a note as our previous note. If the limit as n goes to infinity of an is zero, then the series may converge or diverge. More work, or as we'll build our tool belt, another test that we'll be developing is needed. Okay, so let's jump back into the geometric series, and let's try to now prove rigorously, well, when should a geometric series converge? We need to do some more work and figure out, well, will every geometric series converge? Or is there something we can maybe gain from the divergence test? So let's just consider a geometric series. And so our geometric sequences, I was using this notation, so our constant times r to the n. I'm not going to go through, there's a lot of linearity rules with constants adding two series together. I'm just going to mention them as we go. I don't want to go through stating each one individually. I think it's a waste of time. So I'll just kind of state them as we go and as they come up, just because they should be very natural to you guys if you think of these sums kind of behaving like integrals. So what I mean by that is, well, if I'm multiplying every single term by a constant, we can write this as the constant times the sum of now any expression with a variable in it. And that should essentially make sense. It's saying that, well, I can add up a number of terms, then every term is multiplied by the same constant, or I could just pull the constant out, add up all the terms, and then multiply by the constant afterwards. It's exactly the same as factoring now, really, except we're factoring that c out of an infinite number of terms. So let's just consider this guy. Since that constant isn't going to affect the divergence or convergence, just like we saw with integrals. It's really how is the function behaving? Because if this converges, a constant times a finite number, still finite, still converges. Constant times infinity, infinity. So the fancy trick with a geometric series is this. So let's call this guy S. Is going to be the sum of all of the terms. And that's going to be r plus r squared plus r cubed. And it's going to keep going. And the fancy trick with geometric series is if I multiply that whole expression by r, it's going to be r times r to the n. Well, what do we get? That's just r squared plus r cubed plus r to the fourth, and it's going to keep going. And through the magic of infinity, what's going to happen is if we take, let's say, s minus rs, what do we have left? So I'm taking this guy minus this guy. Well, I'll have r squared minus r cubed minus r cubed, r to the fourth minus r to the fourth. And if I have infinite terms, essentially everything is going to cancel. All we are left with is just r. And so how do I find the sum? We can factor out s from the left and then solve for it. Okay, well, this holds out into infinity. Wasn't terribly precise. So maybe let's try to improve that a little bit, because we don't have quite a good definition for r, and we were taking sums out to infinity, which might be a little sketchy. Let's change it a little bit. Go through that same process, but let's consider the sequence of partial sums. So real quick, our s sub t is just going to be r plus r squared plus r cubed plus, now let's only take finite number of terms. And instead we'll do this properly and take our limit now as t goes to infinity in the end. So then r s of t is now r squared plus r cubed plus, well, in this case, the last term is going to be r to the t plus, we'll have r to the t plus 1, since I took everything there and multiplied by r. And we can't use the magic of infinity by canceling every single term, but what's going to happen if I have s sub t minus r times s sub t? I've got, well, this r is going to remain here. These two terms cancel. The cubes cancel. Everything all the way up to r to the t cancels, but then I'm subtracting off this last guy, minus r to the t plus 1. And so by our same trick, solving for the sequence of partial sums, we get r minus r to the t plus 1 over 1 minus r. And so now here's the question, is what is the limit as t goes to infinity of s of t? So right, 1 minus r. Well, this is going to depend on only t, right? So what happens if, well, if r is bigger than 1, well, this will be a constant, that's a constant. If r is bigger than 1, though, what's going to happen when t goes to infinity? We'll get a minus infinity in the numerator. So let's just mark it as an infinity. In other words, it'll diverge if r is bigger than 1. And it will If r is less than 1, well, now what's going to happen if r is 1/2? So what is 1/2 raised to the infinity? It's just 0. We get that result we essentially previously had. So getting here actually depends on the fact that we need r to be less than 1. What happens if r is equal to 1? This test doesn't quite conclude, but if r is equal to 1, we will get 1 over 1, or excuse me, 1 minus 1 divided by 1 minus 1, so 0 over 0. You could do L'Hopital's rule if you want then for these r's. And then you should find that this one's still going to remain, since the derivative of these guys are ddr. Those two terms will go away, but this numerator will still have r's left in it. And so that term will dominate and go to infinity. Conversely, if you actually just consider the sum, if we're adding up, if r is 1, we're just adding 1 plus 1 plus 1 plus 1. Adding up a bunch of 1s, it's going to go to infinity. One thing to note, I'm actually going to adjust this. These methods that we just kind of derived for our sum of a geometric series. So let's box this, because this is important. And let's write it out. So sum of r to the n equals 1 to infinity, is equal to this. So this is a formula you can memorize if you want, or just kind of know this logic we followed if you want to rederive it and rethink it through. It actually holds in absolute value, meaning that r could be minus 1/2, minus 1/3, and it will still hold for that. Something that gets a little hairy here, because with exponential functions, right, we usually don't allow our base to be negative, right? What is the limit of minus 1/2 or even minus 2 to the t if I take t values that are not discrete, that are not integers? Math gets a little hairy with that. So just kind of take it as my word that this still holds for negative values, as long as we have our ratio, our consecutive ratio that we are multiplying by is less than 1. It could alternate with a plus minus 1 if r was negative as well. Okay, so let's see an example. Let's see, where was the example I had? So let's revisit this guy. We gave a geometric argument just by filling in the consecutive shades of the boxes. It was a geometric argument, a little bit hand-wavy, not too rigorous. But now with our kind of rigorous development of this formula, again, this is just 1/2 to the n. Our consecutive factor we are multiplying by is 1/2. It's less than 1. If I plug that into the formula, we get this. So this is just our r is 1/2. And now it just takes a little bit of algebra. So we have 1/2 times 1 over 1 minus 1/2 is 1/2, which is going to be 1/2 times 2 over 1. And we do in fact cover the whole box if I keep taking pieces of a half away or keep shading pieces of a half. Let's see what happens if we were to only take a third of the box away. So the sum of 1/3 to the n we know it converges since our r is less than 1. And we can plug that into our formula, 1/3 over 1 minus 1/3. Similar algebra again, so we'll have 1/3 over 1 divided by 1 minus 1/3 is now 2/3. And so what do we get? 1/3 times 3/2. So we only get half. So we don't actually cover the whole box. If you want to kind of do a few examples. If we cut it into thirds, I would take that third away. Then you have to cut the remaining piece into thirds. We take that piece away. And keep doing this. I don't know if my work is too correct. I think I'm shading a little bit more. But ultimately, what are we going to end up with? We should only end up covering half the box. Let's see, and we've got 3 minutes. Let's try to do one that's a little more complicated. Let me see. So I had one written down. Yeah. So ultimately what we want to do is we want to practice manipulating some of these expressions and getting it into something like r to the n, or even a constant times r to the n. And the way we can kind of throw these at you, it's really just a test of, do you remember all the algebra for exponential functions? So we've got 2 to the 2n times 3 to the 1 minus n. And the question is, converge or diverge? And if it converges, let's find the limit. So how do we want to manipulate it? We want it to have, to say something to the n. So let's manipulate both terms individually. 2 to the 2n is the same as 2 squared to the n. So I'm factoring out that n because I like the n in the exponent. I don't like these other constants in the exponent. This constant is being multiplied, so this is how we can sort of factor it, so to speak, in the exponential fashion. And that means that that guy is really just 4 to the n. And we like that, something to the n. What about 3 to the 1 minus n? I want it to say something to the n. Okay, so the 1, it's being subtracted. So this is 3 to the 1 times 3 to the minus n. And so really, what is that guy? That is 3 divided by 3 to the n. Or in other words, it's 3 times 1/3 to the n. And again, I have something to the n, constant out front, not a big deal. We like to keep those constants out front as long as I have something to the n now. And so rewriting this guy, and sorry, we're out of time, so let me just finish it up real quick. We have 4 to the n times 3 times 1/3 to the n. We can write as, we can pull out the 3, And now I have something to the n times something to the n, which means I can multiply those two together and write them as that combination to the n. So we have 3 times the sum of 4/3 to the n, and now we see the ratio is 4/3. It'll diverge. You could say by the divergence test, because 4/3, the individual terms are going to infinity, or you could say by our geometric series test, since our ratio is bigger than 1. Any questions? All right, so that sums it up for today. Tomorrow we'll start to learn more tests. How do we deal with a broader array of functions? We'll actually learn p-tests, which are going to be very important for polynomials. And when polynomials appear in the denominator, and it'll work similarly to our integral test, our p-test that we had for our integrals. So stick around if you have any questions. Otherwise, I'll see you tomorrow.
I had the question about the quiz yesterday. So did I just miss